Here we go. Sorry about that. It's sometimes the most simple technology that fails, anyways. This talk will be about sometimes it'll be about core boot and an open source boot system, and my mind just went blank, which is a bit unfortunate. Yeah, I hope you enjoy it, and we have a bit of overtime if you feel like that in the end, and you can start now.
Thanks.
Sorry about that.
All right, so I'm going to talk a bit about core boot and related things. Okay, let's figure out the sound. Where can I go? I can't go there. Okay. So, first of all, who am I? A look at the state of firmware on the PC. First of all, what was there before, what we have right now, and where I think we should go. Going to talk about payloads, which is an important concept in core boot. Some auxiliary tools developed by the same people developing core boot. I have two nice demos that I hope are going to work on real hardware. Some security thoughts, attacks, defenses. A conclusion, some thanks, and links. So my name is Peter Stuge. I'm a self-employed consultant in Sweden, in Malmö, southern Sweden. I know software, hardware, security, and a bit more. I like anything embedded and open source. I discovered core boot back in 2001. It was called Linux BIOS at the time. I was working on building a set-top box for my employer. And it was x86 based, and we needed a firmware. So I thought Linux BIOS looked really good. Unfortunately, we didn't end up using it, but I stuck with the project. Until 2006, I mostly hung out on the mailing list trying to not say all that much, but scope out what was going on and learn as much as I could. I started getting involved in core boot for real at the developer meeting that was held in Hamburg in 2006 in October. These days I work on Flash-ROM, MSR tool, Philo, a bit of K8, that's AMD 64. Version 3 of core boot, some support and marketing. So looking back, in the beginning of the PC we had the BIOS, and we had an 8086 CPU, which did stuff in real mode. And a show of hands, how many people know about real mode and how it works? Excellent, that's about, quick, maybe third, maybe half. Real mode is a processor mode where you have 16-bit registers, so the only data you can handle, the largest data you can handle is 16 bits, from 0 to 65,536. But you had 20-bit addressing, so you could use a little bit more memory than 64K. In the first machines, there were two tape drives that had the operating system and that were going to be booted from. So the BIOS started out really as hardware abstraction. It created a unified interface for accessing these tape drives, loading the software off the tape drive into RAM. And it also did some console stuff, keyboard, video. It had a code for handling the serial port. And all of this happened through software interrupts, where the operating system triggers a special interrupt instruction. The system then jumps into BIOS code and does whatever it needs to do to access the hardware and returns the result to the operating system. This is a task that is pretty slow in the 8086 real mode. So the present, we still have BIOS software in our PCs today, and it's still real mode. It's still 16-bit, and it still has 20-bit addressing. Everything works through interrupt services today as well. There's hundreds of them. The API of the BIOS has just grown and grown and grown. It does floppy and hard drive abstraction. These are just some examples. It does power management abstraction, which is interesting. We're going to come back to that in a bit. But really, the BIOS today, with modern operating systems, it mainly does hardware initialization at the time you turn on the PC, and it starts up the operating system. All the old stuff, the console drivers, the serial port drivers, the floppy and hard drive abstraction, it isn't used by the operating system. It's used by the bootloader to get the operating system started and get the operating system running. But once started up, Linux has all its own drivers for everything. Windows does as well. No modern operating system really calls back into the BIOS using these interrupt services anymore. So what's the problem with this? Well, besides the fact that it's about 30 years old, the BIOS used to be this library where the operating system always initiated the call, and the BIOS was just used to perform whatever action was desired. But then there were developments. The first laptops started coming out, and when you close the laptop lid, you want the system to sort of pause or hibernate and enter APM. This was all realized using system management mode, which is a pretty interesting topic. We're going to go into that a bit. How many people know about system management mode? 3. Excellent, excellent. So this was introduced in the 386SL CPU, pretty old. For laptops, it was Intel's mobile 386 CPU. What happens is, in the beginning, you configure, or the BIOS configures, a handler for events, system management events. And when this event is triggered, the processor stops whatever it's doing completely. It saves off everything it knows about the current state, and it jumps to this pre-configured code, this pre-configured handler. And it's literally like time stands still. The software that was running on the CPU has no way of knowing that the CPU has been into system management mode to do something and then come back. This was all triggered in the beginning by an electrical signal. A new electrical signal was introduced, the system management interrupt signal. But it could also be triggered by software. You can set up SMI traps that invoke this system management mode from an I/O port access or from writes to whatever memory locations you specify. And this is used quite a lot. So this was APM, and APM wasn't really all that bad. It wasn't so powerful, but it was a pretty nice design for the time. And then came ACPI, which we all love. This is the Advanced Configuration and Power Interface Specification by friends at HP and Intel, Microsoft, Phoenix, and Toshiba. The document I found is revision 3 from 2006, 600 odd pages. And among other things, it specifies a virtual machine, has its own bytecode, and it runs in the BIOS. So it's in the BIOS, it's outside the operating system. Really outside the operating system. Yes, at first they did it that way, but it turned out it was too slow. The numbers I've seen was a 5% performance hit from having this virtual machine in the BIOS. So the only solution they came up with was moving the virtual machine into the operating system, and Linux started doing this circa 2001. I've seen the figure 90,000 lines of code to implement this virtual machine, and the fun part is that it still operates completely outside the operating system's security model, because that's the way it was designed to run, and that's the only way it will run. So what do I think about the future? Well, BIOS overview, 78, it was used for tape I/O abstraction. 2008, we have just gobs and gobs of function calls or API calls, and it's real mode. I listened to a presentation from one commercial BIOS vendor. There are only 2 out there at the moment, so they're a bit difficult to work with. They described how their code base has 4,300 files, source code files, in assembly, but it's modular, so it's really easy to work with. There's also EFI. Is starting to pop up here and there. It's already out in Intel Macs and some other Intel machines as well. It's really like a small operating system. Reminds a lot of the old DOS. It has networking stacks. It has a lot of other nice features if you want to develop software and plug into EFI and run during the boot. It's sort of open. The idea is that anyone can download the specs and write these kind of plugins for EFI, but it's not really possible to see what goes on in the core of EFI. Intel doesn't tell you that. So it could be using system management mode for all we know. The Tiana Core codebase, which is the development kit for EFI, is about 250 megabytes. Could be compared with the Linux kernel, which is about 50 megabytes. There's a lot of other bootloaders as well. Grub you've heard about. And Grub is really a bootloader, as is Lilo. Redboot is a bootloader as well, firmware, if you will. It's based on the ECOS operating system, real-time embedded operating system. But unlike EFI, it's really similar to EFI in that respect. But unlike EFI, it's really open source. ECOS is completely open source. There's also U-Boot, which is a firmware for mostly used in smaller systems, ARM, MIPS, power machines. So I say Coreboot is a BIOS replacement. And the BIOS, it does the hardware initialization, and it starts up the operating system. We saw that. Coreboot really only does the first part. It does hardware initialization and nothing else. Then it hands over to a separate program, which is called a payload. The payload takes over and does whatever is supposed to happen. It can start up the operating system, or it can be an application even. Coreboot and the payload, they go together into a single file that is programmed into the flash chip, where the BIOS used to be. So what kind of payloads can we get? We have a lot of bootloaders for different operating systems and storage media. We have Philo, which I mentioned already. It's used to boot Linux or multi-boot kernels from local storage, hard drive or CD-ROM, compact flash if you have that on a IDE bus. Etherboot, GPXE, maybe you've heard of. You can use that to boot kernels off the network. CBIOS is an open source BIOS implementation. So if you really want or, well, maybe need the BIOS stuff, you can still have that, but at least you can have it open source and you can have it in C. Hopefully you won't need it, but for now it's needed to do BSD and Mac OS and DOS, and we've tested it with Windows XP and Vista as well, so it's good. You can also have open firmware as a bootloader payload if you want to, or you can have Linux, which is really the big win. That was also the original idea with Coreboot, or Linux BIOS, as it was called from the beginning. It started out in 1999 at the Los Alamos National Laboratory in the US. A guy named Ron Minnick. He was building a computing cluster with thousands of PC nodes, and he realized that he didn't want the keyboard error press F1 to continue on all of his machines, so he did the only reasonable thing and started writing his own firmware. Yeah. The good thing about that is that Linux has a bunch of drivers for whatever hardware you can imagine, and if you can put that into your firmware, then you have access to booting from whatever. You can boot from wireless, you can boot from iSCSI, you can boot from Mirinet, which is what they used. You can boot from InfiniBand, which is not so easy